Hello everyone. In this section we are covering section 3.2.2, which is on row echelon form. Row echelon form is a special form that a matrix can have, and it's a form that's going to help us solve linear systems, which is the goal of this section. So what is row echelon form? Definition 3.2.3 tells us that a matrix is said to be in row echelon form, or REF for short, if the following two conditions hold. First, any row consisting entirely of zeros is below any row with non-zero entries. And second, the leftmost non-zero entry, which is called the leading entry, in each row is to the right of any leading entry above it. So what does a matrix in row echelon form actually look like? Let's look at example 3.2.4, where we're asked to determine whether each of the following matrices is in row echelon form. And so for each of these matrices, we need to check the two conditions. We need to check condition 1, that any row consisting entirely of zeros is below any row with non-zero entries, and we need to check condition 2, that the leftmost non-zero entry, the leading entry, in each row is to the right of any leading entry above it. Let's start with the matrix in part A. We need to check condition 1. Is it true that any row consisting entirely of zeros is below any row with non-zero entries? Well, in this matrix we have a row consisting entirely of zeros, the second row, but it is not below all rows with non-zero entries. In fact, there is a row below that row of zeros that has non-zero entries. And so that first condition is not satisfied. And so we can already conclude that this matrix is not in row echelon form. In part B, we have a 3x4 matrix. Let's start by checking the first condition. Do we have a row consisting entirely of zeros in this new matrix? We don't. And so already condition 1 is satisfied. Next, we want to check condition 2. We want to check that the leading entry in each row is to the right of any leading entry above it. Let's first identify the leading entry in each row. In the first row, the leftmost non-zero entry is this 3. In the second row, it is 5. And in the third row, it is this 1. Is it true that the leading entry in each row is to the right of any leading entry above it? Well, that 5 is certainly to the right of the 3, but the 1 is not to the right of the 5. This 1 is not to the right of a leading entry above it, of 5. And so the second condition is not satisfied, and so this matrix is also not in row echelon form. Moving on to part C, we check the first condition. Do we have a row consisting entirely of zeros? We don't, and so condition 1 is satisfied. Condition 2, do we have that the leading entry in each row is to the right of any leading entry above it? Well, the leading entries are -1, 4, 7, and -1. And here we can see that each leading entry is to the right of any leading entry above it, and so condition 2 is also satisfied, which means that this matrix in part C is in row echelon form. Both conditions are satisfied. Moving on to part D, we want to check the first condition. Do we have that any row consisting entirely of zeros is below any row with non-zero entries? We do. We actually have two rows consisting entirely of zeros, and they're both below any row with non-zero entries. And so condition 1 is satisfied. Is condition 2 satisfied? Well, the leading entries are this -1 in the first row and this 8 in the second row. And 8 is to the right of the -1, the leading entry in the row above it. And so condition 2 is also satisfied, which means that this matrix in part D is in row echelon form. Next, in part E, we have an augmented matrix. We want to determine if this augmented matrix is in row echelon form. First, do we have any rows consisting entirely of zeros? We don't, and so condition 1 is satisfied. Second, do we have that the leading entry in each row is to the right of any leading entry above it? Well, in the first row, the leading entry is this 4, and in the second row, the leading entry is this 1. That 1 is actually to the left of the 4, the leading entry above it, and so condition 2 is not satisfied. And so this augmented matrix is not in row echelon form. In part F, we have another augmented matrix, and so we're again going to check the two conditions. Condition 1, there is no row consisting entirely of zeros. Condition 1 is satisfied. Condition 2, where are the leading entries? 1, 1, and 3 are the leading entries, and here the leading entry in each row is to the right of any leading entry above it. Condition 2 is satisfied, and so this augmented matrix in part F is in row echelon form. And so we've seen that the matrices in parts C, D, and F are in row echelon form. And we can see that all of them have a nice collection of zeros in the bottom left corner. And these zeros in the bottom left corner, they all form a bit of a staircase pattern. Now let's look in particular at the augmented matrix that we have in part F. This is one we've seen before. Note that the augmented matrix in part F above corresponds to the linear system we solved using back substitution in example 3.1.4. And so it turns out that the linear system corresponding to an augmented matrix in row echelon form is easy to solve using back substitution. Now, we would like to take advantage of this fact in order to solve any linear system, not just one whose augmented matrix is in REF. In general, the augmented matrix of a linear system is not in REF. And so the question is, can we transform an augmented matrix that is not in REF into one that is in REF without changing the solution set of the underlying system? As it turns out, we can, by using elementary row operations. And so next, we will talk about these elementary row operations.